first of 8 modules, Critical V-Ray Settings Part 1, we're going to be looking at two major V-Ray features that I believe are not only some of the most critical to V-Ray users, but also some of the most challenging to understand. And these are the irradiance map and image sampling. They are two of the most commonly depended upon features in V-Ray, and because of their complexity, they are certainly two of the most often asked about features in various V-Ray forms. In fact, if I had to pick which two features were the most difficult to understand for the average user, it would probably be these two. But when you break these features down into their most simple form and apply them to certain types of scenes, I believe that they're really not too terribly difficult to understand. And so in this module, I'll try to make understanding these areas of V-Ray as painless as possible. Now, as I'm sure you've noticed, there are two modules that have been given the title Critical Settings. By labeling these first two modules as critical settings, I'm not at all implying that other settings that we'll be covering in the remaining modules aren't important. I'm simply placing additional weight on certain features that I believe are so fundamentally important that they warrant discussion early on. And I do this because I believe that just as important as what is taught is the order in which the material is presented. So in these first two modules, I'll cover some of these critical settings. And as an additional note, we won't be getting into the material editor this early on, because while materials are obviously a critical part to any scene, I would prefer to leave these additional variables out of the equation, which would really only confuse things early on. So some of the features in the material editor, while critical, will be discussed later on in Module 3. Now, we can't really get into a discussion on either of these two major features until we briefly talked about the concept of indirect illumination. So what is indirect illumination? Well, take a look at the following image, and in this scene, all the light comes from one source, which happens to be a V-Ray sun, a new feature to V-Ray version 1.5 that we'll look at much later. But what's important is that there are two major types of light that you're seeing in this image: direct illumination and indirect illumination. Direct illumination is the illumination that directly strikes the surface after leaving the light. In other words, it hasn't yet bounced or been reflected. Indirect illumination, on the other hand, is, as its name implies, indirectly illuminating the surface after first bouncing off another. So direct light is seen striking the surface of the pool deck here, the pool water, some of the grass in the back, and indirect light can be seen illuminating the shadows, the areas of the side of the house. And just because the surface is struck with direct light, that does not mean that indirect illumination is not playing a role. In fact, once direct light has bounced off the surface, it may end up striking the same surface later as indirect light. However, its impact is much less than that of direct light. So if I open the Render Scene dialog box in Max, you can see that through the Advanced Lighting tab, we have the option to use advanced lighting features such as radiosity, which employs the use of indirect illumination. Of course, we can also use the Advanced Render Engine Mental Ray that ships with Max, but we're obviously focused on the use of V-Ray, so I'll switch the render engine from the default scanline render engine to V-Ray. And when I do, you'll see a bunch of rollouts appear. Now, I'm a huge fan of customization, though I don't recommend it too much for new users. But one thing I would definitely recommend any user begin doing from the start is arranging the V-Ray rollouts in order of their frequency of use. And this is simply because over the course of a project, you can end up spending an enormous amount of time navigating to the rollout of choice by having to constantly close rollouts or scroll up and down just to find the one that you need. But rather than confusing things here by rearranging rollouts, I'm leaving them as is with the exception of these first two rollouts, which you'll never need to open once you've got V-Ray loaded and ready to go. So I'm going to take these first two rollouts and move them to the bottom. Let's look at another scene. This is a simple scene with just a few primitives. Direct light can be seen here, and indirect light can be seen in the areas in the shadow over here. And let's look at this same scene without any indirect illumination, and this is what you get. You get total darkness in the areas that we previously had indirect illumination. And now let's look at the same scene again without any direct light. So here we have the same scene, and the entire scene is lit solely by skylight, which is a term for ambient light that bounces off the particles in the atmosphere. So this scene is completely lit with indirect illumination. So indirect illumination, also known as global illumination, or more simply GI, is approximated through the use of complex algorithms that require an incredibly large number of calculations to complete. And just to look at a few examples here, these are some algorithms that are running behind the scenes, not necessarily in V-Ray. These are just some sample algorithms, but this is what's going on behind the scenes in V-Ray. There's a couple more examples, and as you can see, it's pretty complex stuff. This is really not what you need to know. All you need to know is that this stuff is going on behind the scenes. And like all advanced render engines, V-Ray has several options for making these approximations, which is what these algorithms are doing. And each of these approximations have their own distinct advantages and disadvantages. The indirect illumination rollout here controls which of these methods are being used. So to enable indirect illumination in V-Ray, all I need to do is enable this switch, the on switch, here in the indirect illumination rollout. Now, within V-Ray, indirect illumination is categorized in two different areas. Indirect illumination that is directly visible by a camera's view or visible in the reflections and refractions from other objects is referred to as a primary bounce. Indirect illumination that is used in overall calculations of GI, basically everything else but a primary bounce, is referred to as a secondary bounce. And V-Ray uses several different methods to approximate these bounces. And these different methods contain parameters that control the quality and the approximation, as well as the time it takes to make these approximations. So when I enable indirect illumination with the on switch, I am given access to the primary bounces and secondary bounces. And if I click on the drop-down menus for each of these, I see that there are several options for each. In this first module, we're going to be concentrating on the irradiance map. On the second module, we're going to be talking briefly about the quasi-Monte Carlo and the light cache. We aren't going to be referring to the photon map at all because I believe it's not as effective as the other methods. It's slow if you want to achieve the same quality. So we'll first look at the irradiance map, and then we're going to talk briefly about image sampling and anti-aliasing because it's directly tied into the results you get from the irradiance map. And once we finish with image sampling, we'll jump over to light cache, and we'll go on from there. So what is an irradiance map? Well, an irradiance map is a very complex subject, and you could write a book on it if you wanted to. In fact, there have been many lengthy papers written about that very subject. It is simply a tool to approximate GI, and more specifically, it's a method for storing the calculation of radiant energy or light, which strikes a set number of points in 3D space. In 3ds Max and in V-Ray, energy, light rather, is considered nothing more than energy, so it's equated in those terms. And with a 3D point map of the stored illumination values in the irradiance map, V-Ray can approximate the amount of illumination that arrives at every point on every surface, and thus better determine how to color the pixels in the rendering. That's what it's all about. What is the final image to look like? And what makes algorithms behind the irradiance map so great is they approximate GI more accurately in areas that require more detail, such as shadow transitions in places where different surfaces interact. And they are applied less accurately in places where detail is not needed. And this is usually in flat, open areas. And to do this, V-Ray renders a camera's view in a number of different passes, starting with a low resolution pass and progressively working up to a higher resolution pass. And within each of these successive passes, V-Ray determines if GI is good enough in each area of the rendered view, and if it's approximated well enough by the samples taken in each of these passes. If it is good enough, it won't take any more samples in further passes. If it's not good enough, it will continue to take more samples in future passes. Well, that explanation is fine and dandy, but what do I mean by samples and what do I mean by passes? So let's return to this scene, and I'm going to open up the irradiance map rollout. And when I do, you'll see some values that are different from the default value. At the top of the irradiance map rollout, there are numerous settings that control the samples and the number of passes, and thereby controlling the quality of the final rendered output. And at the very top, you'll see some presets. These presets control other variables, other settings down in the basic parameters section. And unless I have the custom preset set, I cannot even change individually the settings that you see ghosted out in the basic parameters section. But I want to switch this to custom and set the minimum rate to 0 and maximum rate to 0, and render this out. Before I do, I want to point out that I have the Show Calc Phase option on, which enables me to see the irradiance map as it's being calculated. So with a custom preset and a min-max rate of 0, I'm going to render this out, and I'm going to stop it right here. And when I do, I'm going to zoom into the rendered window so I can zoom in closely on one particular bucket. Now, if you were to go to the system rollout, you would see that there is a place where you can specify the size of each bucket that's rendered. I haven't changed that. It's set to 64 pixels across and 64 pixels top to bottom, and I'm not going to touch that. If I go to the Common tab in the Render Scene dialog box, you'll see that the final rendered output is 640 by 480. Now, going back to the Render tab and the irradiance map, I see that my min-max rate is set to 0, and when I have the min-max rate set to 0, that is telling V-Ray that I want my irradiance map to be the same resolution as the final rendered output, which, as I just mentioned, was 640 by 480. Now I'm going to count the number of pixels, or not pixels, but the number of dots that I see across in each bucket. When I do, I can count that there are 64 dots across and 64 dots top to bottom. What does that mean? Well, that means that for every pixel in the final render output, there is a dot. And that means that my irradiance map is the same resolution as the final rendered output. I'm going to zoom out, and when I zoom out, I can see that there would actually be 10 buckets across. And when you multiply 10 times 64, that's how you get 640 pixels across. So therefore, when min rate and max rate are both set to 0, I will have one pass with an irradiance map that is equal to the final render output. Well, let's say that I want to decrease my min rate to -1. What does that mean? That means that my irradiance map will be half the resolution. My initial irradiance map in the first pass will be half the resolution of the final rendered output. And I can see that when I render this out again and zoom into one particular bucket. I can do the same thing over again and calculate the number of dots I see from left to right. And when I do, I will see 32 dots and 32 dots top to bottom. That means that my bucket, which contains 64 pixels, contains 32 dots within my irradiance map. Therefore, when the min rate is set to -1, my irradiance map is half the resolution. So what this means is by having a min and max rate, I can have two different passes. First pass at -1 is half the resolution of the irradiance map. And during that first pass, V-Ray tries to determine and takes samples and tries to determine if the irradiance map that's calculated is good enough to approximate the GI in all the different areas that it takes samples of. If it's not, then on the next pass, when it determines that it's not, it will take more samples at a higher resolution, which is set at, since max rate is set to 0, that higher resolution is actually the same as the final rendered output. So I can continue to decrease the minimum rate value here. I'll set it to -2, and when I render it again, you'll see that the dots that make up each individual bucket are larger. I reduce it again to -3, and the dots again become larger, and the irradiance map resolution is lowered, at least on the first pass, with each successive drop in the minimum rate value. And I can continue to drop it until the quality of the irradiance map on the first pass is ridiculously low. And I would never really want to set this minimum rate that low, but the point is when you separate the min and max rate, that increases the number of passes. So with a min rate of 0 and a max rate of 0, I'll have one pass. With a min rate -1, max rate of 0, I'll have two passes, and so on. So to summarize, with each successive pass, V-Ray determines if the GI in each area of the rendered view has been adequately approximated by the samples taken in the previous pass. If so, then no further samples will be taken, and if not, more samples will be taken on successive passes. So with each successive pass, the resolution of the irradiance map is actually doubled, and therefore V-Ray can potentially take 4 times the number of samples as the previous pass. Now it would be impractical and far too time-consuming to calculate a sample for every pixel in the rendered view. So instead, V-Ray will take what it believes is the required number of samples to approximate the GI, and it will interpolate all the areas in between. And the results of these samples are stored in the irradiance map, and the accuracy of the irradiance map is directly dependent on these number of samples and the quality of those samples. Now let's take a look at what these samples actually look like. I'm going to set my min and max rate both to -3. I'm going to render this out using the show samples option. This will allow me to actually see the samples as it's being rendered. So when I render this out, I see these dots appear throughout the scene. And these dots represent the actual samples that are being taken. Now, when I have this set to a min and max rate of -3, I'm only having one pass being rendered. And because there's only one pass being rendered, V-Ray is not being adaptive or intuitive in where it places these samples. It's placing these samples pretty evenly throughout the image. But if I switch my minimum rate to -4 or -5 or something lower, it's going to add more passes. I'm going to set this to -5 and re-render this, and notice that there's 3 passes now, and that the final image that shows the samples shows much fewer samples in areas where it does not need the extra detail, and shows the samples closer and tighter together in areas where more detail is needed. And so it's this adaptive quality of the irradiance map that makes it so great. The ability to be adaptive to each particular scene and apply more sampling in areas where detail is needed and less sampling in areas where detail is not needed. So let's render the scene out with a minimum rate of -5 with the show samples option turned off and see what kind of quality we get, and compare it to a minimum rate of -3. And so this is what we get using a minimum rate of -5. I'm going to switch over to a minimum rate of -3 and turn off the show calc phase, re-render this, and you can see that there is very little difference in quality, but there is a significant improvement in the amount of time it takes to render these two different images. So what are some good min and max rate values for a typical visualization? Well, as I mentioned earlier in the introduction, I believe knowing V-Ray well means knowing how to troubleshoot. And ideally you want to use settings that give you the quickest rendering times with the fewest number of undesirable effects that often plagues visualizations. And lower quality settings obviously means faster render times, but what might be good for one scene may not necessarily work for another. But nonetheless, the presets offer a great place to start, and if you experiment just a little bit, you'll probably find a preset that provides the best mixture of speed versus quality for any particular scene. At 3AS, we usually use very low test renders of large scenes. We use low presets for test renders of small scenes. We tend to use medium presets a lot for production renders, whether they're large or small. And if we determine that a medium preset is creating too much noise or too little detail, we can switch to the high preset, and that generally gives us a good base to work from. But as you'll see in upcoming sections, there are settings within the irradiance map that should be addressed besides just the min and max rates. One of these settings, and probably the most critical in the irradiance map rollout besides the min and max rate, is the hemispheric subdivisions value. Now this is a particular setting that confuses a lot of people, but it's really simple when you break it down. At each point that a sample is taken, rays are traced out from those samples, virtual rays, and they're used to determine the amount of light arriving from each direction, and they're used to improve the quality of the GI approximated at each point. Now the more rays that are traced, the more accurate the sample becomes. And in simplistic terms, if you placed a virtual hemisphere above each sample as shown in this image and trace rays from each sample through each subdivision of the hemisphere, you can see that the more subdivisions, the more rays that are traced. Now this particular image is a very rough graphical representation of this process. A more actual account of the process can be seen in this image, which is from Greg Ward's paper called Irradiance Gradients. And this gives a pretty good idea of how the rays are being traced and how the hemisphere is broken down. Now the actual number of rays that are traced is equal to the square of the hemispheric subdivision values, although this can change depending on the settings within other areas of V-Ray, such as the quasi-Monte Carlo sampler rollout, which we're going to discuss later. By default, the hemispheric subdivision value is set to 50. However, I would really recommend avoiding such a high value because it can create some excessive render times. You always want to experiment with any scene, but a good number to start with would be 20. And if this value gives you what you want and doesn't create any problems in the GI you're seeing, then don't increase this value. If you do find problems such as splotches, then you might want to experiment with small increases of this value, but you might want to avoid values above 50 because it can really increase your render times at the benefit of very little gain in quality. And likewise, values below 20 should really be avoided because the savings you're going to find in render times are not worth the great loss in quality you're going to get from lowering this value. As an additional note, the hemispheric subdivisions value has nothing to do with the number of samples that are taken. The number of samples taken is dictated by such values as minimum rate, maximum rate, and some of these others over here, color, normal, and distance threshold. The hemispheric subdivisions value only controls the quality of the samples. Now, what happens in between all those samples that are taken? Taking all these samples is great, but if you don't have any information to go from to create the final rendered image in between these samples, then what's the point? Well, the next setting that we're going to be talking about, the interpolation samples, that's where the information is filled in between. The word interpolate actually means to insert between other things or to estimate values of data between known values of data. And we can look at this in a very simplistic form by just looking at a simple circle. Now, when you create a circle, 4 vertices are created in that circle automatically, but there is an interpolation rollout with the circle that allows you to reduce the interpolation value from 6, which is the default value, to 0. When you do, you'll see that the circle becomes a diamond, and that's because there's no interpolation, there's no guessing between those known vertices. So if we increase the interpolation, we are increasing the number of steps, number of guesses or estimations in between the known values. And the same thing is happening within the irradiance map. The interpolation samples value determines how many of the irradiance map samples that were taken will be used to estimate the GI between those samples. Let's look at these 2 images. In the image on the left, MN and max rate of -5 was used, which results in just a few number of samples as shown on the image on the right. This is clearly not a good rendering, and these aren't good settings, but it does help to illustrate the effect of interpolation. Now let's look at 2 more images of the same scene. In the image on the left, the only thing that was changed was the interpolation samples. A value of 2 was used, which means that only 2 samples are used to determine the GI at any point. And the result clearly is a cell-like appearance to the GI. And if you superimpose the samples on the rendered image, you can actually see that each sample is centered on a uniformly shaded cell. Now, the size of each cell lies directly between the 2 samples that were used to determine the shading on each side of the cell's border. Let's look at a few more examples. In the far left image here, a interpolation samples value of 3 was used. In the middle image, a value of 5 was used, and in the far right image, a value of 10 was used. And as you can see, increasing the interpolation results in greater smoothing or blurring of the GI. Now, what are some good values to use? The default value of 20 works great in most situations. You could try increasing this value to 30 to remove some blotchiness that might persist in your GI. You could also try reducing it to 10 to bring out some detail in your GI. Now, blotchiness and lack of detail are 2 very common problems that people run into. So this particular setting, the interpolation samples, can really help to improve your renderings. The next irradiance map setting that I want to talk about is the detail enhancement setting. And as its name implies, it can help to bring out some detail in your scene, but it comes at a hefty price in rendering time, and I would only recommend using it if all the other things you've tried have failed. And the settings that we've talked about up to this point in the irradiance map really play an important role in bringing out detail, and if those settings aren't right in the first place, adding detail enhancement here may not necessarily have any effect. And to see just what effect this has versus other settings, not only in the irradiance map but other settings in V-Ray, let's walk through a sample exercise. If you want to follow along with this exercise in Max, you can open up the file called building01.max. Now, if I render the scene as is, you'll see that there is a significant amount of detail lost in the reveal lines and in the grout lines of this building. And if I open up the irradiance map rollout, you can see that I'm using a low preset. Now, I'm going to enable detail enhancement and render the scene again. And as you can see, there's almost no improvement in the detail of the grout lines, even though the rendering time increased almost 6-fold. this would be a really poor use of detail enhancement, and there's something definitely wrong with the scene that's preventing the detail from popping out. Now I'm going to try setting I'm going to turn the detail enhancement off and change the Radiance Map preset to high and render the scene again. And when I do, you'll notice that there is still no noticeable improvement in the detail of the reveal lines. And you could use some of the settings within the detail enhancement section to improve the effects, but the default settings are really sufficient for most situations, and improving them here just won't be worth the cost of the increased rendering times. This demonstration does not mean that detail enhancement is not a worthwhile setting. It's just that its effects are negated by some other problem, some other setting in V-Ray, and we need to find out what that is if we want to bring out this detail. Now we're going to depart a discussion on irradiance maps, and we're not going to come back until we talk about animation in a layer module. But for right now, we need to look at the area that's really causing the problems with the scene, and that would be the image sampler. So let's talk about image sampling. Now, with the exception of post-rendering effects, the very last step in any rendering process is anti-aliasing. Aliasing is just a term that describes the imperfections in the rendering process caused by color changes that are too drastic and that occur over too small of an area to be adequately depicted by the pixels that define that space. And anti-aliasing filters can improve the jagged edges that are caused by aliasing and therefore improve the overall rendering. And it does this by adjusting the pixel color according to the amount of pixel coverage that is specified in the filter. Now, V-Ray supports all the standard max filters and covers a few additional filters that apply to only V-Ray. And if you want to refer to the Insider article entitled Anti-Aliasing and its Side Effects, you can learn more about anti-aliasing and what type of filters you might want to use. I'll briefly mention a few that you might want to use for general purposes. But before anti-aliasing can even be applied, V-Ray has to sample each pixel to determine what objects lie in a scene within the boundary of each pixel, and therefore what color to apply to each object in the area of the pixel. And the image sampler is a tool that this is done with, and therefore it plays a critical role in the final render output of a scene. Now, without the necessary image sampler configuration, high quality settings in so many other areas of V-Ray and 3ds Max are negatively affected. Such was the case in the last exercise. So how is image sampling applied and how is it controlled? Well, there is an image sampler rollout, also known as the anti-aliasing rollout, and in this rollout there are 3 image sampler options: fixed, adaptive subdivision, and adaptive QMC. We're going to look at each of these in depth and see which sampler type is best for each particular situation. So let's look at the fixed image sampler first. Now this is clearly the most simple of the 3 different samplers, and there's only one setting that can be used, the subdivision setting. Now to see the effects of this particular filter, let's look at the following image. This is just a simple box, and if you zoom into the edge of the box, you will see that the box has a very jagged edge, very noticeable jagged edge, and this is because I turned off anti-aliasing. So anti-aliasing could have been used and really always should be used, but it wasn't used here to help show the effect of image sampling. But how does V-Ray perform image sampling, and how can you control and improve it? Well, a problem in any digital rendering is that the edge of objects never align to the edge of pixels. And when that happens, you're always going to get a jagged edge unless you use anti-aliasing. Well, let's take a look at the following image. And in this image, we see a simplified and blown up version of the box's edge using a 4x4 grid. In other words, 16 pixels total. The dashed line that you see here represents where the edge of the box wants to be displayed, but because of the limited resolution of a computer screen, this edge can never really be perfectly represented. So with an image sampling using one subdivision, one sample is taken at the center of each pixel, and the samples are shown with red dots here, and the color that a sample detects is the color that is assigned to the entire pixel. And as you'll see, one subdivision is usually far from sufficient for a decent transition in any rendering. Now let's look at these 2 images. These 2 images represent the before and after effect of using a subdivision value of 2. When using a subdivision value of 2, each pixel is subdivided into 2 subpixels horizontally and vertically, and a sample is taken at the center of each subpixel. Now, because of the greater subdivisions, you can better approximate the true location of the box's edge. And after determining what percentage of pixels receive the background color and what percentage receives the box's color, the image sampler adjusts the color of the entire pixel based on this percentage. And in the image on the right, you can see that the two pixels that have three subpixels covered by the box receive a darker color than the two pixels that have only one subpixel covered. And we'll look at one more example here. And in this example, we're subdividing each pixel 3 times horizontally and 3 times vertically. So every time you do this, every time you increase the subdivisions, you can better approximate where that edge of the object appears and thus better apply coloration to the final rendered output. Returning to the render scene dialog box, you'll notice that for each image sampler type that is selected, you have a unique rollout that appears. And again, in the fixed image sampler rollout, we only have one setting, the subdivision setting. Now, the fixed image sampler is the most predictable of the 3 different image sampler types because it applies the same number of subdivisions everywhere to every pixel on the screen. And the primary disadvantage of this is that because it does, it's not adaptive. It cannot apply lower settings to certain areas or certain pixels and higher settings to other pixels. And this sampler is best utilized in scenes where a great amount of detail is necessary, either structurally or in maps, or there's a large number of blur effects. And as a general rule, we only use this at 3ds when 75% or more of the rendered image contains areas where we need this kind of high level of detail. And in these cases, we recommend using the fixed image sampler, but when that 75% percentage is not met, then we usually use one of the other two. And by not using the image sampler on scenes with a large amount, you run the risk of V-Ray guessing wrong as to which areas should receive greater sampling. So let's return to the previous exercise we were using and see how changing the image sampler can really improve the detail that is brought out in the irradiance map. If you want to follow along, you can open up the file called building02.max. And this scene by default uses the adaptive subdivision sampler. And again, it uses a low irradiance map preset with no detail enhancement. So if I render the scene, this is what the image looked like. This is what it looked like before, and I'm just showing this again to show what it looks like right now. And if we change the image sampler to fixed and change the subdivision value to 4, this means that each pixel will be subdivided 4 times horizontally and vertically, thereby giving 16 subpixel samples. And the improvement is pretty drastic. Notice that when I render this again, the render time increased approximately 2.5 times, but you see a lot more detail brought out in the irradiance map. And now if I choose the detail enhancement option under the irradiance map and render it again, my render time increases again, but you can now see some improvement using the detail enhancement that you couldn't before. And now this image sampling increase brings out this detail enhancement. Now let's look at the adaptive QMC sampler. This sampler is similar to the fixed sampler with one major exception. Like its name implies, it's adaptive, so it can apply a range of possible subdivisions based on the min and max values that you specify here. So in areas where less detail is needed, V-Ray is likely to use the minimum subdivision value, and in areas where greater detail is needed, V-Ray is likely to apply the maximum subdivision value. By default, V-Ray applies a min and max value of 1 and 4, and this provides decent quality for test renders. For production renders, I would recommend using values such as 3 and 6, but I would also definitely recommend not going much higher than 6 because the image sampler can really have a significant impact on your rendering times, and values higher than 6 are going to give you excessive render times with very little increase in quality. I'd also recommend not separating the min and max values by more than 3. Doing so can just open V-Ray up to applying incorrectly guessing where in the scene you need more detail and where you don't need as much detail. And you can see just how similar the fixed and adaptive QMC samplers are by rendering the same scene with both sampler types and making the min and max value in the QMC sampler the same value as the subdivisions value in the fixed sampler, and when you do so, you'll find almost identical renderings. So when should you use the adaptive QMC sampler? Well, this sampler really is best suited for scenes where a high level of detail is needed or there are a lot of blurry effects. And as a general rule, I would recommend using this sampler when your rendered image has up to 75% of its space requiring this kind of detail. More than 75%, I would recommend using the fixed image sampler simply because the small amount of time you're going to save with the QMC sampler is not worth the risk of having certain areas of your scene undersampled. But in either case, you should always experiment to determine which sampler works best for each particular scene. One additional note about the QMC sampler has a great feature here, the Show Samples option. And this actually allows you to see where V-Ray applies the different subdivision values in a scene. And in this image, you can actually see two different colors that represent where the min and max values were used. In this particular image, there's two different colors and two different subdivision values used. And in this image, the min and max values were set to 1 and 3, thereby showing 3 colors. And in this final image, the min and max values of 1 and 4 were used, and therefore 4 colors are shown. And the brightest color indicates the area of greatest subdivisions. Now let's look at the final sampler, the adaptive subdivision sampler. This sampler is really unique and is really great because it's the only one of the 3 that allows you to take fewer than 1 sample per pixel. So notice that instead of using a term min and max subdivision, it's using the term min and max rate. And this means that instead of describing the samples as a certain number of subdivisions per pixel, it's instead saying that pixels are sampled at a rate of X pixels for every 1 sample. What does this mean? Well, at a rate of 0, 1 sample is taken per pixel. At a rate of 1, there are 4 samples per pixel. At a rate of 2, there are 9 pixels. On the flip side, at a rate of -1, it's saying that there are 4 pixels for every 1 sample. At a rate of -2, there are 9 pixels for every 1 sample. And because of this, you really have the ability to reduce render times in a scene. But this particular sampler does not work for all particular scenes. It really only works in scenes where there are few blurry effects and a minimal amount of highly detailed areas can be found. So in scenes with large areas of smooth surfaces, the sampler really works good. Now I want to end the discussion on image samplers by showing 3 different images and telling you what I would recommend using for each of these 3 different images. In this first image, I would recommend using the fixed image sampler simply because there's so many areas where a high level of detail is needed, such as the crown molding, and it's these areas that detail might be lost if you use one of the other 2 samplers, the QMC or the adaptive subdivision sampler. In this particular image, I would use adaptive QMC because while there is detail that's needed throughout the scene, it's really confined to just a few areas. The palm fronds in the trees and these lines here in the building, there's a large amount of area in this particular image that detail is not needed, such as the sky and the water. So you could definitely save some rendering time by using the adaptive QMC sampler here. And again, you might just need to experiment to figure out what setting you might need to set the min and max values at. In this final image, this is a great example of when you would want to use adaptive subdivision. And this is because there are many areas of large flat smooth surfaces such as the ceiling and the furniture. And even where there's detail needed, such as the paintings, it's really not in an area of the scene that detail is really critical. If it's not shown in the painting, it's not going to really be detrimental to the scene. Well, this concludes Module 1, and as a summary, we talked about 2 major concepts in V-Ray, the irradiance map and image sampling. The irradiance map is a great choice for your primary bounce engine because it gives you the ability to use great detail, which is needed for the primary bounce. For the secondary bounce, you simply don't need the same level of detail, which is why the irradiance map is not even an option. In the next module, we'll take a look at the light cache and Quasi-Monte Carlo, 2 possible options for both primary and secondary bounces. Some things to remember from Module 1, the hemispheric subdivisions value plays a critical role in the quality of your irradiance map samples. 20 is a good value to start with, and you should experiment with small increases up to a maximum of 50. to smooth out any blotchiness in your samples, try increasing the interpolation samples up to a value like 30. To reduce the smoothing effect and bring out detail, you could try reducing this value to 10. Detail enhancement is another possible solution to bring out detail in your scene, but just like other high quality presets, it's only a worthwhile option when you use the appropriate image sampling. And for image sampling, these are some good guidelines that I would recommend following. Now, clearly we didn't cover every option and setting in these two features, but we really did cover the most relevant and the ones that you should focus on in your work.